Our next speaker is Amanda Mejia from National University of Singapore, speaking to user-friendly spatial Bayesian modeling for task fMRI.
Hi, thank you, Jean. So I'm Amanda Mejia from Indiana University. I've been spending the past year at National University of Singapore. And today I'd like to tell you about a tool that my group has developed for spatial Bayesian modeling and task fMRI called BayesfMRI. Okay, so just a short outline. First, I'll explain what I mean by spatial Bayesian modeling, since this may be an unfamiliar technique. And then I'll tell you about how to take a Bayesian approach to the classic GLM for task fMRI analysis. And then just tell you a little bit about our BayesfMRI R package. And we have a poster on this today and tomorrow, so you're welcome to stop by and learn more. Okay, so first, what are some of the differences between frequentist and Bayesian statistics? So frequentist is really classical statistical analysis where we use the observed data to estimate the parameters of our model. Typically, this is done by maximizing what's called the likelihood. The nice thing about frequentist approaches is that they are usually fast and straightforward, easy to compute. Think about things like a sample mean. The downside is that any noise in the data is reflected in our estimates. And our main technique to reduce that noise is to collect more data, which of course in imaging is easier said than done. In Bayesian statistics, we do something which is very natural, which is to take into account our prior beliefs via what's called a prior distribution. And so estimation is now done through the posterior distribution. And this reflects the updated beliefs about those parameters based on the data. So the nice thing about Bayesian statistics is that it results in better, as in more accurate estimates, but it can be intimidating because it has a reputation of being difficult and or slow. So I'm hoping to convince you that, at least in this context, it does not have to be difficult or slow. So in terms of task activation, what do we mean by prior beliefs? So there's a few prior beliefs we may have. We may believe that patterns of task activation should be pretty similar across subjects, for example. And we could encode this belief through a prior on the voxel-wise or vertex-wise activation amplitudes. And so the prior variance would reflect the variability in the population. And we could use like a hierarchical Bayesian model to fit this kind of, to use this kind of prior. But we may also believe that the patterns of activation should be similar for nearby or proximal locations. And we can encode this belief through a multivariate prior across the locations, where the prior covariance represents the spatial dependence between neighboring locations. And the spatial Bayesian models, which I'll be talking about today, use this type of prior. So what is a spatial prior? It can seem a bit mysterious. So imagine we have 6 data locations on the cortical surface, and we want to estimate a latent spatial map of activation or anything else, which we would denote beta. So the beta can be organized as a vector, and a spatial prior is simply a multivariate prior with a multivariate mean mu and a covariance matrix sigma. And sigma is encoding our prior beliefs about the spatial dependence between those 6 locations. Often we want to use sparsity, so we will only want to assume direct dependence between neighbors, and this is computationally advantageous. So an example of a prior that's often used in fMRI or in any kind of imaging context is a multivariate Gaussian prior with a sparse inverse covariance. So that's one example of a spatial prior, but it's really just one example. It just happens to be the type that we commonly use in imaging. Okay, so you are probably familiar with the GLM for task fMRI analysis. And so a spatial Bayesian GLM is just a generalization or an extension of the classic massive univariate GLM. So GLM refers to a general linear model, and the goal is to estimate amplitude and areas of activation during a task or stimulus. In the classic GLM, we're fitting a separate model at every voxel or vertex in this massive univariate approach. Whereas in a spatial Bayesian GLM, we're fitting a single model accounting for spatial dependence via spatial priors, and this is going to gain us both accuracy and power, particularly for first-level modeling. Okay, so if I would just write this in equation form, we're relating the observed bold signal at a particular location to the amplitude of activation under every task at that location based on a particular design matrix. So this is just the classical GLM. We're fitting this model at every voxel or vertex V. And so, of course, we have an image. We don't have a single voxel. So what we do is then combine across all of those models to form a statistical parametric map, or SPM, where we can do hypothesis testing and correct for multiple comparisons to get areas of activation. So this is the familiar approach. So in a spatial Bayesian GLM, we start by just writing all of those V models as a single model, but that doesn't really give us a spatial model. That's just a different equation. But when we put a prior or a series of priors on those maps or images of activation, we get a spatial Bayesian model. One of the things that we've done in our paper is to identify areas of activation through the joint posterior distribution via an excursion set approach. And this is, I think, an important aspect of spatial Bayesian modeling because it allows us to avoid multiple comparisons and to therefore avoid multiple comparisons correction, and to fully utilize the spatial dependencies at both the estimation and the inference step. And this actually gets us a dramatic gain in power, so much that often we find that we're identifying areas of very subtle activation. So another thing that we can do is to specify a minimum effect size of interest, say 1% signal change, 0.5% signal change, for a motor task, maybe 2% signal change, and only identify significant areas of activation that are above and beyond that minimum effect size. So in a paper we published in 2022, we did an analysis using data from the HCP to look at the reliability as well as the power associated with this spatial Bayesian approach. And so here I'm showing estimates and areas of activation for 3 different subjects from the HCP motor task, the tongue contrast. And what we found is that the Bayesian approach, the spatial model, had much higher power, but also really high reliability across multiple visits. So we can see the unique functional topography of these 3 subjects that's really reliably identified at both visits. This approach is also scalable for multi-subject analysis, so we can simply fit the model at the individual level and then combine it in a principled way to get group average contrasts. And so based on 45 subjects, you can see here the estimates of activation are actually quite similar to the classical massive univariate approach, but the areas of activation are much broader, so we have much higher power even with 45 subjects. And we did Bonferroni correction in that main figure, but also if we do FDR or permutation testing, the Bayesian model still has larger areas of activation. So the power is actually quite high, and this is one of the reasons that we often specify a minimum effect size of interest, so we don't identify these kind of broad, very subtle activations. Here's also a plot showing that for smaller samples, the gain in reliability and accuracy for second-level analysis is significantly higher for the spatial model. One other thing that this facilitates is the use of prevalence maps. So if we imagine different ways that we could combine data from multiple subjects to do population-level inference, there's a couple of ways that we could approach this, but the traditional way is to take our subject-level activation estimates, right, and then produce average maps, and then do inference on those. But another approach that we could take, in theory, is to take our subject-level activation our subject-level activations, and then average those to get prevalence maps. And one of the reasons this is not historically done is because we don't have enough power at the first level to produce prevalence maps. But with this Bayesian model, we actually do have decent power at the first level, and so prevalence maps are something that we can start to look at. So on my poster, we will illustrate a demo, but you can also access the full demo. This is a QR code to link to that. It's also available at my lab's website on our software page. And there's a few other highlights of the package that I'd like to just briefly mention. The functions are compatible with SIFTY data as well as GIFTY and NIFTY. The model fitting is very fast through C and C++, our NLA, and parallelization. We can easily do visualizations via the SIFTY tools package. Pre-whitening is done in a spatially varying way in order to produce valid inference in first-level analysis. And then I also want to mention a new feature, which is spatially varying design matrix to allow the assumed HRF to vary across the brain. And with that, I'd like to just make a brief shout out to the Sifty Tools package, which is really Damon's baby, and he's done an amazing job of developing this tool, which has allowed us to work with Sifty data as well as Gifty data directly from within R, which has been really what's made this work possible. So with that, I'd like to thank you, all my collaborators, and also just invite you to learn more about the opportunities to join our group, and invite you to come talk to me at our poster if you're interested in learning more. Thank you.
Okay, thank you for that wonderful talk. So one of the popular questions from our audience is, how do you specify the spatial prior? How do you set the parameters? So in general, how do you specify the prior?
Thank you. So we use a special class of priors called stochastic partial differential equation. I won't say that again, SPDE priors. And these are really nice because they're Gaussian Markov random field priors, so they have sparse inverse covariance and a Gaussian parameterization. But also they are more flexible than some of the older Gaussian Markov random field priors. And so this is a type of spatial statistics that's available within R. And so through our collaborators and through the existing packages, we're able to use that type of prior. That prior is actually built for triangular mesh data, so it's perfect for cortical surface analysis, but we've also recently extended it to work with volumetric structures as well.
Thank you. Maybe
Oh, and I should say that the hyperparameters of that prior are estimated during model fitting, so we don't have to make any assumptions about the spatial dependence or the variance of the data a priori.
Okay, maybe to just quickly follow up on that, this will be the last question for this talk. Can you comment further on how you avoid multiple comparisons correction using this method?
Yes, so the technique is designed to use the joint posterior distribution. So we actually look for a collection of locations where the probability that all the locations are activated reaches a certain threshold. So we can say that under the posterior, that the probability that every single location exceeds, say, 1% signal change is 0.95 or 0.99. And the converse of that is that the probability that any of them is not activated is 0.05 or 0.01. So in that sense, it controls the family-wise error rate from a Bayesian perspective.
Okay, thank you so much.
Thank you.
I noticed that there are more questions. Please join us after the talk. So thank you once again.